Students, this question is about a DC shunt motor with compensating winding, and there is a computer. So we are talking about a DC shunt motor. What is a DC shunt motor? It is very similar to a DC shunt generator. What is shunt? This means that this is the armature, and in parallel to the armature we have our field winding. Here is RF and here is RA, this is EA, and terminal is here, very similar to a DC shunt generator. But what is happening in this scenario is in generators the current is going out from the armature, but in this case the current is moving towards the armature, and the terminal the IT is into the machine and the current is into the armature, and the field current remains the same as it was for the generators, but the direction of current reverses both for the terminal current and the armature current. This is actually a motor where electrical power, this is the electrical power which is being converted to mechanical power. And the equations for this shunt DC motor, we can see that IF is equals to basically Vt over Rf, and for shunt motors we assume that Vt remains fixed. And what will be the equation here for EA? How much voltage is induced here is actually equals to Vt plus IA RA. Sorry, it is actually Vt equals to EA plus IA RA. This will be the equation for this scenario. So how much voltage? This is the KVL I have applied in this direction. So the internally generated voltage will be Vt, this voltage, minus this drop that is occurring here, minus IA RA. So these are basically, and the third equation that we must know, that the current IT that is coming from the source, there we have a source, DC source Vt, the current coming from that is actually equals to IT is actually equals to armature current plus the field current. So if we want to calculate the field current we know this is how we can calculate it. So these are the fundamental equations for a DC shunt motor, and only for the DC and for the DC generator they become the opposite. The equations, only the direction of the current is changed. Now let's look at the question. It is saying this is the rating 250 volts, 1200 RPM is the motor rating with they have given us armature resistance of 0.06 ohms. What is the armature resistance? This resistance. Field circuit, the total resistance that is of 50 ohms. This resistance is of 50 ohms, and at no load the speed is 1200 rpm. So if we consider N0 to be the no load speed, that is 1200 rpm, the rated voltage, there are 1200, and they are the other thing 1200 turns per pole on the shunt field winding. So what it is saying is, so the no load speed is 1200 rpm, and what it is saying is that if the RF, the value of RF is 50 ohms, that means that IF will be what the value of IF, that is the terminal voltage, 250 volts divided by 50 ohms, that will be 5 amperes. So the field current will be 5 amperes, and at no load speed it is to 1200 rpm. So this means that when our motor is rotating at no load, it is drawing no current, so This is 0, so EA is equals to V terminal equals to 250 volts. So the terminal voltage will be the voltage that will be generated at the terminal. Now the tricky part, or what is the question he is asking, what will happen if I connect a 100 ampere load or a 200 ampere load or a 300 ampere load to the motor. Now what do you mean by connecting a load of 100 amperes to the motor? If this is the motor, it means that a mechanical load is connected which will cause the terminals of the motor to draw 100 amperes current. If this is the current that motor is drawing, so it is asking what will be the speed of the motor, what will happen to the speed of the motor when a 100 ampere load is connected. Load is actually mechanical, it is requiring a certain torque, but we measure it through how much current it will cause the supply to give it to the motor. So whenever we will be loading our motor, its speed will gradually slow down. So it wants to know how much the speed will change. Now for the motor, we know that we have the fundamental equation K phi omega. Now there are two options here. The method will be similar, but the options will be either we use this formula in which omega is in radians per second. So the speeds that we have is in RPM, we have to convert in omega and we can solve and then revert back. Or we can say that the same formula, for example, we apply the conversion ratio, we can say that it can be written as like this. So this means that I have just applied the conversion to this formula. Now I am using the speed in RPM. Now please listen this thing to carefully. For a speed N1, there is a voltage EA1 that is being generated inside the motor when it is rotating at speed N1. And for an N2, I can say that there will be another voltage that will be generated inside the machine at speed N2. And as the machine constant is same and the flux is also same for both scenarios, we can write this equation as EA1 over EA2 equals to, we can write this relationship. And if we know this relationship, if we know the values at one speed, we can easily, for example, if we know the values, three of values, we can calculate the values at the other speed. So what is the question? The question is now at the rated speed, that is 1200 RPM. We know how much is EA1, that is 250 volts. Now for another condition, for a loading condition, if we are able to calculate EA2, if we are able to calculate when, for example, our motor is loaded for 100 ampere, how much is EA2? If we are able to calculate EA2, we will put the values in this equation and we can calculate the new speed of the motor. What will be the new speed of the motor? And that is what he is asking about. So for the part 1, when it says IT equals to, for in question part A, it is saying 100 amperes. So it is saying that the load is of 100 amperes. Now in 100 amperes for the machine, we know if the current is 100 amperes, some of the current is divided here and some of the current goes to the armature. So the armature current is actually IT minus IF. IF we know is 5 amperes. So this will become 95 amperes. How is IF? This is here we have calculated IF equals to 5 amperes. The current, the terminal divided by RF. Okay, so if we have this value, then what will be EA2? It will be equals to VT minus IA RA, and V terminal we know it's the rated voltage and it's the supply voltage minus 95 ampere into 0.06 ohms. This is also given. Where is given? This is the value of armature resistance. So EA2 will become 244.3 volts. Now after loading, the internal generated voltage has become 244 volts, 0.3 volts. So the question was, when the voltage has fallen to this value, what will be the speed of the motor at this case? So this, as I have previously shown, we know that for EA1, for N1 we have EA1, for N2 it should be EA2. So the value of actually the EA2 is, so N2 is actually equals to EA2 over EA1 into N1. N1 rated speed 1200 RPM. EA2 that we have calculated here 244.3 volts, and EA1 was at 1200 RPM, it was 250 volts. So the speed N2 will be 1173 RPM. That is, this speed has fallen down from 1200 to 1173 RPM because of the 100 ampere loading. The next part states is, if now the input current is 200 ampere, same as previously, now we will solve this again for IT equals to 200 amperes. And for IT equals to 200 amperes, if you solve it like this scenario will be, this will result in N2 will become 1144 RPM. So this is how you have solved this, and also then you can plot the value for the DC motor, the torque speed characteristics. For the DC, for any kind of DC machine, the terminal characteristics are actually the relationship between torque and speed. So in the part D, it is stating that plot the torque speed characteristics of this motor. So the plot to plot the torque and speed characteristics, we must be knowing what is the relationship of the power, electrical power and the mechanical power. For the motor, torque and speed is what is important for us, because that is the mechanical output that we are getting from the motor. So actually for the DC motors and for the DC machines, the power converted inside the machine is actually EA IA equals to torque induced into speed. So what this means is, electrical power is actually EA IA, and the mechanical power is actually equals to torque induced into speed. So in this scenario, and I will consider one case, that is the case number 1, the part A that we solved, to find out the torque for this speed, how much torque was induced. So we can say that the power converted, and this power converted is critical if you know the idea of the machine power flow diagram that will be covered in other examples also, that there is a power converted where electrical power is actually equals to the internally generated mechanical power. So if we have torque induced equals to EA IA divided by speed. In this case, the internally generated voltage is EA2 that we have calculated. So this is actually EA2. What is IA? That is, we have also calculated IA, that is 95 amperes. So this is actually 244.3 volts. This is actually equals to 95 amperes. Now what is the speed that we have calculated? It is 1173. But it is, if I will put this value, this is wrong because in the formula it is omega. So what I need to do, I have to convert 1173 into RPM into radians per second, and for this it is the formula is very simple. We multiply it by 2 pi by 60. 2 pi by 60, this will convert this value to radians per second. So torque induced, if we put all these values, the torque induced for this certain load and the speed at this speed will be 190 Newton meters. You should put all these values. So you need to remember the conversion if you have to convert RPM into radians per second. This is the conversion formula. I hope it helps. Thank you. Assalamu alaikum.